Hi guys, you hear me? Please, I need to hear this.
We can hear.
Yes.
Okay, good, because I just had to change my earbuds out, and the last ones I used didn't work, so I had to limp along with a set of earbuds that were broken for months. We doing okay, guys?
So
You
far,
okay?
so
Yes,
good.
sir.
Wonderful. I'm sorry, guys. I really am. You guys have been absolutely wonderful. I just wanted to take a time that I have to say that you have made this easy for me. It's been a pleasure. I've looked forward to coming here, even at 8 o'clock in the morning. I really have looked forward every Monday and Wednesday to coming in and seeing you all and seeing your bright, shiny faces at this time of the morning. And I really have felt that this has been a great class. And it's to your credit, ladies and gentlemen. You all, I do mean this from the deep bottom of my heart. You are all going to be successes, and it has been a great honor teaching you. Now, this is where you come in and you say, "Oh, Mr. Popovich, you have been so great. Oh, Mr. Popovich, we couldn't have had a better teacher."
Oh,
Crickets.
Mr. Popovich.
Crickets.
Oh, Captain, my captain.
I'm getting crickets here.
You shouldn't have.
Okay, guys.
We're just too flattered.
This is something, what we're going to be discussing today is something that, yeah, you could blow it off. The actual page, the actual results section you're going to have to fill out is going to have 90 questions or so. And really and truly, you could blow it off, say, hey, I've got my grade that I want so far, but the trouble is this is going to help you in so many ways. It is giving you practice. It's giving you practice in how to do Lewis dot structures as well as doing VSEPR. So with that in mind, guys, I hope that I can get this off and doing it right. All right. Okay. First off, we're going to change some conceptions that you have of Lewis dot structures. Up to this point, you've been told that you can only have 8 electrons around any atom. Is that true? Maria? Is that true? Taylor, is that true? We have to disavow you of that conception. We limited it to 8 in introduction because we wanted to keep it simple for you. Now, what you have to understand is you can have less than 8 and you can have more than 8. You just have to give in to that, okay? So the first thing we're going to do is, in order to do VSEPR, you have to be able to draw Lewis dot structures. Have to. No other way behind it, okay? So let's get into doing Lewis dot structures. And as soon as I get the right page up here. All right. Lewis is a brilliant man. He came up with a definition, a new definition for acids and bases. And the other major thing he came up with is this concept. And basically, if you haven't heard this from me before this, I'm telling it to you now. Chemists are lazy. If they don't have to do something, they're not gonna. Whether you're gonna have to drag them, kicking and dragging, or kicking and screaming into doing something that is totally useless. And what Lewis came up with is, you know, those inner electrons don't do a damn thing. So if they don't do anything, why do I have to draw them? So what he did was he ended up drawing only the valence shell electrons, and he represented them with dots. So if you look at oxygen, Maria, do you have a periodic table in front of you? Guys, you should have one. Guys, find the periodic table. Jeremiah, you got one in front of you?
Yes, sir.
Okay. How many electrons in the valence shell does oxygen have?
Six.
Has six.
Yep.
So the way I'm going to put the dots around the oxygen, I'm going to put one in each side of this oxygen atom. One here, 2, 3, 4. Then I'm going to start pairing up the electrons. So I get 2 on one side, 2 on the other. So I have a total of 6 dots around my oxygen. And already I know a lot. If I tell you that bonds are formed by each atom contributing 1 electron, how many things can bond to oxygen? Christine? Look at what I've drawn. Look at how I've drawn oxygen. If I tell you that bonds are made by each atom contributing 1 electron, how many things can bond to oxygen?
2.
Already know that. I draw nitrogen. Let's see. I'm gonna get somebody. I've got the same 5 people up here. Kylie. If I draw nitrogen, it has 5 valence electrons. So how many things can bond to nitrogen?
3.
3. Okay. So do I need to give you any more examples on how to draw the atoms? Are we pretty good with this? Anybody confused? Speak up now. Because I'd like to get through some of this stuff. Now, if I have a molecule, I can also represent it with a Lewis dot structure. And the way I do that is if I put 2 electrons between my atoms, that indicates that there is a bond between those atoms, that each one of the atoms has contributed 1 electron. So we have a bond. So if I have methane, CH4, I can represent that by having a carbon, 2 electrons, hydrogen, carbon, 2 electrons, hydrogen, carbon, 2 electrons, hydrogen, carbon, 2 electrons, hydrogen. Are we good with this? All right, so we need to have some rules. And I'm gonna go slow through this so that you can write them down, because I'm going to be asking you questions on some molecules. First thing you do is from the molecular formula, you write down the elements. Second rule, when you write them down, you put the least electronegative element in the center, if you can. Now, if you have something like water, H2O, obviously hydrogen is less electronegative than oxygen, but hydrogen can only have one thing bonded to it, so it can't be in the center. So in that particular instance, we have to put the oxygen in the center. If you can, put the least electronegative in the center. So we got our step 3, and that's going to be to add up all the valence electrons. If we have something like phosphorus trichloride, phosphorus has 5. There are 3 chlorine molecules. Each one of those chlorine has 7. So 3 times 7 is 21. 1 times 5 is 5. That makes 26 valence electrons. If I have an ion, I have to account for the charge. Say I have SO4 2-. The sulfur gives me 6. Each oxygen gives me 6. So there are 4 oxygens, 4 times 6, 24, plus the 6, 30. But I have a -2 charge. This means that SO4 has 2 more electrons around it than the neutral atoms do. So I have to add those 2. So I get 24 from the oxygens, 6 from the sulfur, and 2 more from the charge for a total of 32. Similarly, if I have NH4, the nitrogen gives me 5. Each one of those hydrogens gives me 1. So 5 plus 4 is 9, but it's NH4 plus. I have to take away that electron to make only 8 valence electrons. Are we good about rule number 3 now? Cal, shake your head because you've been through this before. Are we good? Seriously, any questions about that one? Now, the next thing you do is you put 2 electrons. Those are the bonds. You put 2 electrons between each of the elements. Then you subtract the number of electrons used from the original valence electrons. So rule number 4, you put 2 dots between each one of the elements. Those are the bonds. If you don't put those 2 dots there, then those 2 elements aren't bonded to one another. Rule number 5, you subtract the number of electrons you used in bonding from the original valence electrons. 6, you're going to fill all the terminal atoms with pairs of electrons. Those are called lone pair electrons. Note, because hydrogen only needs 2, you can't put any more around it because the 2 in hydrogen are going to be used in bonding. Rule number 7, you subtract the lone pair electrons, the ones around the terminal, from the remaining electrons left. If there are any electrons left over, they go on the center atom. Now, this rule, next rule is you're going to see, we're going to violate it in a second or two. But normally, if the center atom does not have 8 electrons, you take a lone pair from one of the terminal atoms and place it between that terminal atom and the center atom. What you have done is you've created multiple bonds. Last step, check to see that every atom has 8 electrons around it. Questions? Questions so far? Okay, how many of you have been through this semester, have been through VSEPR and or Lewis? I know everybody in my class has. You've been through Lewis anyway. Is this new material for the rest of you?
Yes.
Maria, you're shaking your head. You've had this?
Yes, I have.
Okay, good, good, good. So I've got a mixture of half and half. Don't worry, we're going to get through it. It's really, really not all that hard. Has everybody got the rules written down somewhere?
Yes, sir.
Okay, note, if you have a halogen has 7 electrons around it. So it only has 1 unbonded electron, or I'm sorry, 1 unpaired electron. So it can only bond to one other thing. Same with hydrogen. Hydrogen only has 1 electron. It can only have 2. So you can't put any more electrons around the hydrogen. So hydrogen and halogens will kind of end the chain because you can't bond it to anything but one thing. There's a puzzler. You're in the United States. You're a sales rep, and you have to drive around the United States. But you can only enter the state and leave the state one time. where do you start? You have to start in Maine because, believe it or not, Maine is the only state in the United States which only has a border with one other state. So you can only leave Maine. You can't get back into it because you would have had to have gone through New Hampshire and left New Hampshire. So it's kind of isolated out there. In the same way, if you have a halogen or a hydrogen, it ends the chain, just like Maine ends the chain of the United States.
What about Hawaii? How would you get there?
Swim.
All right, fair.
All right. So we're going to start this off. We're going to deal with SO2. I like SO2 because it really gets all of the elements that I need of the Lewis dot structures. I have the molecular formula. I'm going to write the elements down. I'm going to put the least electronegative sulfur in the center. Second step, I count up all the valence electrons. Sulfur has 6. There's only one of those atoms. So sulfur contributes 6 valence electrons. There are 2 oxygen. Each one of those has 6 valence electrons. So there's a total of 12 valence electrons for oxygen. I add those 2 up. I have 18 valence electrons in SO2. Next step, I have to put 2 dots between each of the O's and the S. I started up with 18. I have now used up 4. So I have 14 left. Okay. My next rule says I put the electrons around the terminal atoms. So this oxygen only had 2. I put 2, 4, 6, 8, 10, 12. When I put them around the terminal atoms, I put them around them in pairs, and the terminal atoms can only have 8. So I've added up 12 more, 2, 4, 6, 8, 10, 12 more electrons. I started off with 18. I used 4 in bonding. That left 14. I just put 12 around the terminal atoms. That leaves 2 more left. Place the remaining electrons around the center atom. Now I'm going to look at my molecule. Does every atom have 8 electrons around it? T, what does not have 8 electrons around it? T?
Yes.
What element does not have 8 electrons around it?
Oxygen.
This oxygen has 2 bonding and 2, 4, 6 lone pairs. 2 and 6 are 8. This oxygen has 2 bonding, 2, 4, 6 for 8. What's the element that does not have 8 electrons around it? I don't know. It's a good answer, T.
Yeah, I don't know.
Okay, Kristen?
Sulfur.
Sulfur. So my rule 9 says if sulfur doesn't have 8 around it, I'm going to take one of these lone pairs around the oxygen and shove it in between the oxygen and the sulfur to make a double bond. Now everything has 8 around it. I have a good Lewis dot structure. Questions? Questions on this, ladies and gentlemen? Good, because you're going to do the next one. Oh, except there's one thing. I hate dots. Do you know why I hate dots? There's a very good reason for me to hate dots.
Because they're too easy.
They're too easy. I have a molecule here, right? I have my SO2 that I've drawn. Okay, I have my SO2. I have this one. Right? Isn't this a nice little SO2 molecule? By the way, I flunked Etch-a-Sketch when I was in kindergarten. All right, let me ask you this. Do you see this guy here? Is that a dot or is it not a dot? Is it a dot or not a dot? Do you know when it becomes a dot? When you want to plead with me, oh, Mr. Popovich, but that's a dot. So I hate dots. So I prefer you just use lines. One line will represent two dots. And besides this, when you get to organic chemistry, this is the way they draw molecules in organic chemistry. Now, if you do something like this, undo. If you do something like this, it is not wrong. If you put the dots out for the lone pairs, it's not wrong. It's also not wrong if you put the lines out for the lone pairs and use dots for the bonds. You should not, your teacher should not mark you off for that. Emphasis on the should not. Talk to them. When you're doing Lewis dot structures, talk to them and ask them if your preferred method of drawing Lewis dot structures is okay with them. Pin them down because you don't want to sit there and argue after you've taken the test. All right. Okay, clear all drawings, stop share. We're going to go back to, all right, we're going to now do one on your own. CO2, Kylie. You're writing these down on a piece of paper. Which one goes in the center?
Carbon.
Very good. Okay. Natalie, how many valence electrons does this have? How many does oxygen have?
Oxygen has 6.
How many oxygens do we have in this molecule?
Oh, we have 2.
So what is the total number of valence electrons contributed by oxygen?
12.
So to that, we're going to add how many from carbon?
4.
For a total of how many valence electrons, Natalie?
That would be 16.
16, good. Taylor, you're off the hook, Natalie. You did a
Thank you.
successful job. Taylor, okay?
Yes.
What do I do now? I've got my valence electrons counted. I think that's what this next thing is going to say. I got 16 valence electrons. Now, what is the next step for me to do?
You bond the atoms.
I bond the atoms. I put 2 electrons between each one of the atoms. So that's used up how many, Taylor?
That would be 4.
How many? I started with 16. How many do I have left?
12.
12 left. Okay, Aaliyah. I've got 12 electrons left. What do I do with them now?
Put the rest around them.
Around?
Oh,
Around the oxygens. So I'm going to put them around the rest of the oxygens. Aaliyah, do I have one element that doesn't have enough?
carbon.
How do I get more around the carbon?
Add from the oxygen.
I'm going to add from the oxygens. Good. So I have 2 options. I can either make 2 double bonds by taking 1 pair of electrons from each oxygen, or I could take both of them from the 1 oxygen. Both of these are legitimate Lewis dot structures. One is better than the other. One is better than the other. It turns out the 2 double bonds are better than the triple bond, single bond. But it's going to take something called formal charge, and you're going to have to wait until you get to lecture to understand what the difference between the 2 are. If you want to know, I will tell you after class, okay? Unless I have some extra time here and there. Right now, all the elements have 8 electrons around it. I'm good. Are we fairly good with this? We fairly understand this? Okay. Garrus, Adrian, Aaliyah, and Monica, I want you to do H2O. Draw the Lewis dot structure. Paige. Larry, Alexis, Bethany, I want you to do that is that is SiO2. I want you to do that one. All right, where am I at? Okay, Garrus, did I get you already? Kyle. Christine, Maria, and Jeremiah, do COS. Corey, Kylie, T, and Natalie, I want you to do CO3, 2 negative charge on it. Taylor, you're on your own. CN -1. I ran out of people, Taylor. Bethany, did I give you one already?
Yes.
All right. I'll be back in about 5. Do you need more time? Are we good, guys, or do you need more time? Talk to me, guys. Do you need more time? Thank you, Natalie. Thank you for shaking your head. Natalie, which one did you have?
Number 4, CO3 2 minus.
Okay, good. Tough one. 18, okay, I understand. What structure did you come up with?
Do you want me to just show it?
Sure, if you've got a piece of paper there, you can show it. Put it
Can you
right
see
up to
it?
the screen.
Oh.
I can't. Exactly right. Exactly right. She's done a couple things. Natalie, could you put it back up on the screen again? She's done a couple things there. One of which is the Lewis dot structure is correct. The other thing that she did that I didn't need to tell her, she knew how to do it anyway. When you have an ion, what you do is you enclose the entire Lewis dot structure in brackets and you put the charge outside of the brackets. Anybody have any question about the CO2? Go ahead, Natalie, put it down.
Okay.
Anybody have questions about the CO2 or CO3, 2 minus? SiO2. Who had that? Come on, guys. Let's get through this, all right? Who had SiO2?
I did,
Who's I did?
Larry.
Larry? Okay, what did you come up with SiO2?
It pretty much looks exactly like the CO2 one.
Exactly.
Um,
It is exactly like the CO2. Si has 4 electrons. Oxygen has 6 each for a total of 12 plus 4 is 16. It's going to give you the same Lewis dot structure as CO2. You can either put 2 double bonds between the Si and the O2, or you can have 1 triple and 1 single filling the terminal atoms to fill out the 8. Does anybody need to see the structure? Do I need to make somebody put it up to the screen? Okay. Those of you that did COS.
Is the same structure with carbon in the middle.
Same structure with carbon in the middle. You can have 2 double bonds from the carbon to the oxygen and 2 double bonds to the carbon and the sulfur. Now, I'm going to stop share here for a second. You can actually draw more molecules. Okay? Because you can do this one. Okay? Now, if we do triple bonds, is this molecule, I told you I was horrible at Etch-a-Sketch. Is the second molecule different than the third? Is the second different from the third?
Yeah.
So basically you have 3. You have 3 different Lewis dot structures. Now, to complicate matters further, you could switch these elements around. You can put oxygen in the center. You can put sulfur in the center and have these same 3. So ultimately, you would have 9 possibilities. Again, there's something called formal charge that allows you to tell you which one's the best. And if you actually do the formal charge on all 9 of them, you would find that, let's see, that would be 3. This one, I believe, is the best. Nope, sorry. 4 and 4. Yeah, sorry, I lied to you. If you do the formal charge thing, that one would be the best. But again, I'm going to let your lecture instructor talk to you about formal charge. Questions about normal Lewis dot structures?
Yeah, I've got a quick question. So is the reason you're able to switch out the center atom in that like example because the electronegativity was so close?
No, no.
Or you can do
Basically-
that for any compound.
No, basically, you can draw legitimate Lewis dot structures, changing out the elements. But literally speaking, when you do the formal charge, when you do it, you'll quickly see why one is preferred over the other 8. Does that make sense to you?
Yeah, thank you.
The other, all 9 are legitimate Lewis dot structures, but there's one that's the best. And by doing formal charge, you basically prove that when you put the least electronegative in the center, you end up with the best molecule. Does that make sense now? I can go through formal charge if you'd like, guys. I have until 12:30 to be at Gibbs campus. Maybe we will go through it in a few minutes, but for right now, we're not going to deal with it, all right? Screen share, we're going to go with this thing. Okay. I'm sorry, I just have a whole lot of stuff that I have to deal with. All right. The molecule BeH2 exists. It exists. It is a fact. Now, beryllium has only 2 valence electrons. Hydrogen only has 1 each. So there's only a total of 4 valence electrons in the system. Because of that, and I know that this exists, there are circumstances where you can have less than 8 electrons around the center atom. You just have to understand that that's the way it is. If you don't have the valence electrons, you just have to draw it the way it is. There's nothing you can do about it. Sometimes you're going to have a molecule with an odd number of electrons. What has to happen when you have an odd number of electrons is you have to have one of the electrons be by itself. Since it's by itself, you are never going to get 8 around that particular element. When you have an odd number of electrons, what happens is you have something called a free radical. A free radical is much more reactive than a molecule that does not have a free radical. If I would change one of the O's to an N, then I would have a much more stable molecule because I don't have that free radical. So that's the second reason you could have an exception to the octet rule. Are you with me so far? All right. Let's consider this. Okay. And in order to consider this, I'm going to go new share for a second. I'm going to stop share. And I am going to No, wait, I can do that. I'm going to do this. And show. Okay. I have to talk about formal charge. All right. I'm going to insert new slide. All right. Formal charge. Basically, all formal charge is the charge on the atom as it exists within the molecule, as opposed to how it exists just being the atom itself. And formal charge is equal to normal valence electrons minus lone pair electrons. Notice I am talking about lone pair electrons, not lone pairs. Lone pair electrons plus bonding electrons divided by 2. And the reason you're dividing the bonding electrons by 2 is because they're shared. So that is what formal charge is. Now, the best molecules have 0 formal charge. But if the atoms have a charge, the negative charge must be on the atom with the most electronegativity. And that kind of makes sense. If the atom has more electronegativity than the other atom, then you want the negative charge to be on the more negative one. Does this make sense, guys? All right. Now, I'm going to draw a BF3. And I have 3 ways to draw that BF3. I can draw it with the double bond being between the boron and the fluorine, the top one, the left one, or the right one. Boron has 3 electrons. Each fluorine has 7. So I have 24. So if I'm drawing this, I'm going to go boron, F, F, F. So I had 24 electrons. I just used up 6. So I have 18 left. My next rule, put them around the terminals. Okay. I've used up 18. I have none left. Now my rules state that I take this one and move it into there so that I have a B F. Double bond, F. Understand that there are still terminal atoms around the fluorines. Now, if I go and do the formal charge on boron, boron has 3 normal valence electrons minus, it has no lone pairs, but it has 8 bonding. Over 2. So I have my boron has a charge of -1. This fluorine here has 7 normal valence minus it has 4 lone pair electrons plus 4 bonding electrons, that's a plus. Divided by 2. So it has a charge of +1. Now, can somebody tell me what the most electronegative element in the periodic table is?
Fluorine.
Fluorine will never, ever, ever have a +1 charge when it is next to a fluorine. So as a consequence, what happens is, because of that fact, this structure that I've circled is favored. It's favored, and it has been demonstrated through bond lengths. If I have a double bond, I have a shorter bond length. So if I'm looking at an X-ray crystal of BF3, if this were the correct structure, I should have one bond length shorter than the others. That doesn't happen. It exists like this. So because of that, we know that this is the correct structure, and you have to accept the fact that a center atom can have less than 8 electrons. Are we good, guys? Do we kind of understand what's going on? Now, not only can they have less than 8, but they can have more than 8. I have xenon tetrafluoride. And yes, the inert gases can react. If I do xenon tetrafluoride, xenon has 8, the 4 fluorines have 28. So I have 36 electrons that go around. If I count them from the bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 26, 28, 30, 32. So with all of the electrons around the fluorines and one bond between the xenon and the fluorines, I still have 4 electrons left over. They have to go somewhere. They go on the center atom. So the next to last rule I had, if after you put the electrons around the terminal atoms, if you have extras, they go on the center atom. Now, I'm gonna have to go find something in a second. Okay, I gotta find something. Nope, Greg's old PC. Pictures. Want to see my vacation pictures? Be more interesting than this crap.
Yeah, all right.
Yeah, I'm sure you would. Actually, I just got told this weekend that my Australian New Zealand vacation was canceled. I'm not happy about that. Come on. Okay, good. Okay, do you see the periodic table here? Everybody's seeing the periodic table I have.
Yes.
All right, now we have to go back into our quantum mechanics. Remember that these hydrogen and helium's 1s, lithium, beryllium is 2s, the boron through the neon is 2p, neon, sodium, magnesium, 3s, aluminum through argon, 3p. Then remember we did the funky thing. We went to 4s, then what is this orbital from scandium to zinc? Come on, somebody has to remember.
D.
E.
What's D?
3D.
3D. So in actuality, these orbitals, the 3D orbitals, are in the same shell as the 3s and the 3p. So if I'm down on this level, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, from this level down, I have d orbitals that are in the same shell. Does that make sense to you? Kylie, does that make sense? So I can use those d orbitals to stuff extra electrons into my molecule. And that, in effect, is what happens. So if I have an S, because that's in the 3p, I can incorporate 3d orbitals to accommodate extra electrons. So sulfur can have more than 8. Phosphorus can have more than 8. What about nitrogen and oxygen? Is there a 2d orbital? You're right, Kylie, there is not. There's not a 2d orbital. So everything on the second level cannot have more than 8 electrons. Everything in the third level and below can. Did that make sense to you guys? Come on, talk to me. Garrus, did it make sense to you? Anybody confused about that? If I have phosphorus pentachloride, guys, I've got 5 chlorines. Remember, chlorine cannot be bonded to more than one thing. So all 5 of those chlorine, if I have the molecule PCl5, all 5 of those chlorines must be bonded to the phosphorus. That automatically means that I have phosphorus at 10 electrons, more than 8. But again, phosphorus is in the 3p level. I can incorporate d orbitals to accommodate those extra electrons. Adrienne, you good with this? Monica, is this kind of making sense? So again, we're following the rules. We're following my original rules. And my original rule said, if I have extra electrons, after adding them around the terminal, I'm going to put them on the center atom. I didn't even realize I had that. I can have as many as 12 electrons around the center atom. You're not going to get to 14 and beyond. 12 is the limit. So again, another example of how I have gotten more than 8 electrons around my center atom. Do I have any questions about this, ladies and gentlemen? I can draw a PO4 ion. I can draw it such that I have all these charges. I can draw it just single bonds. That's a valid Lewis dot structure. But I can also draw it with one double bond. And by putting that one double bond in there, I relieve the formal charge on the ion. I relieve the charge on the phosphorus and the oxygen with the double bond. So this has less formal charge than this one does. When I'm talking less formal charge, I'm talking about the number of atoms in the molecule that have charges. Or if within the molecule you have a multiple charge on one of the elements. Those are not favored. Guys, I really, if you are not understanding this, people that are in my lecture, you have the lecture videos for Lewis dot structures. I recommend Organic Tutor or Khan Academy. It depends upon which one that you can relate better to. Both of them are excellent sources. If you're not understanding this, I would go and view the videos on one of the two of them. Any questions on Lewis dot structures? I'm hearing crickets, guys. This is your chance.
Are you going to give us the easy ones in the test?
Huh?
Are you going to give us the easy ones in the test,
Of
or are they going to
course.
be complicated?
Don't
Okay,
I
good.
always?
Yeah.
Okay. We're going to shift to something else right now. And that is something called VSEPR. And that stands for valence shell electron pair repulsion. And guys that have me for lecture, I'm sorry, but you're going to get the same slideshow. We're going to go through VSEPR theory, bond angles, and we're going to talk about polar bonds and polar molecules. I have to see whether I need to talk about hybridization. Hybridization is easy, at least for this portion of it. Okay. Monica, do you have a little brother? Taylor, do you have a little brother?
No, I have a little sister.
Oh, almost as good. I could speak as a little brother because I was a brat. My brother hated me. Taylor, when you were put in the back seat of the car, did you kind of bunch up together in the center? Or did you get as far apart from your little sister in that car as you could?
As far apart as we could.
All right. Now, if you're in the house with your little sister, do you want to be in the same room with her?
Ah. Yeah, I'm actually close with my sister, so.
You're not a good example. Maria, do you have a sister or brother?
A little brother.
Okay, do you want to be in the same room as him?
No.
You want to get as far apart from, again, I keep on telling you, chemicals and atoms are no different than people. Atoms want to get as far apart from one another as they can. And the reason for this is each atom has a electron cloud that's around it. So you got a negative cloud that's surrounding this atom. So they want to get as far apart. If you had a magnet, the magnets would want to push away from one another. So that's basically what's happening when we're dealing with VSEPR. And we're going to use this theory to determine what the structure of the molecule looks like. So they want to get as far apart from one another as possible. And from that, we can predict the shape. We need some vocabulary. You will see these things called electron clouds or electron domains. Either one will work. They're synonymous. And an electron domain is any lone pair. All lone pairs count as one electron domain. It counts as one electron cloud. If it's a lone pair, it counts one. If it's a single, double, or triple bond, they count as one electron cloud. If you think about it, this makes sense because if you have a single bond, double, or triple bond, they're in the same direction. It may have more density, more electron density, but it's in the same direction. And we're counting like directions here. So you have to know that an electron cloud or electron domain is each lone pair counts as one domain. Every bond, whether it be a single, double, or triple, counts as one electron cloud. A lone pair is a non-bonding pair of electrons that are on that particular atom. They belong to that atom and are not shared at all. Bonding pair is an electron pair that is involved in bonding. So if I'm looking at this molecule, this double bond counts as one domain. This single bond counts as one domain. This single bond counts as one domain. This electron pair counts as one domain. So I have 1, 2, 3, 4 domains around the A. And we're looking at center atoms here. You will not ever have to deal with terminal atoms in this particular scenario. Okay? When we're considering how these things orient themselves in space, we consider all electrons, lone pairs, and the bonding pairs. When you're naming the electron geometry, we only focus on the positions of the atoms. This is an important concept. When I'm talking about electron domain geometry, I consider all electrons, lone pairs, and bonding. When I'm talking about molecular geometry, I'm only talking about the positions of the atoms. I'm only dealing with the bonding. So if I am dealing with one lone pair, I can't see that for a molecular geometry. My overall electron domain, the lone pair is out here, so I have 1, 2, 3, 4 electron groups or 4 domains. So my electron geometry is going to be tetrahedron, but I can't see the electrons. I can't see the lone pair. All I can see are the atoms. So all I can see is a shape that looks like trigonal pyramidal. If I have 2 lone pairs, I can't see either one of them. My molecular geometry is bent, but my electron geometry is going to be tetrahedral. So to determine the electron geometry, all I got to do is count the number of electron clouds in the Lewis structure. I have the Lewis structure of ammonia. It has 1, 2, 3, 4 electron clouds. This lends itself to a tetrahedral electron geometry. So important slide, guys. If you have 2 electron clouds around the center atom, your electron cloud geometry is going to be linear. 3 things around the center atom, 3 clouds around the center atom, trigonal planar. 4 things around the center atom, it will be tetrahedron. 5 around the center atom, trigonal bipyramid. 6 electron clouds around that center atom, you will have an octahedron electron geometry. So you're going to either have to memorize it, put it on a sheet of paper if your professor allows you a cheat sheet. You're going to have to do something on it. I would put this in your notebooks. By the way, we need to talk about the final sometime. So I need to make sure I do 2 things before I leave this class today. I need to specifically bring up the results section because it's kind of funky. And I also need to talk about the final. Are we good, ladies and gentlemen, on this slide? Did you got enough time to copy it down? Important slide. Now, if I'm dealing with molecular geometry, all I'm dealing with are the atoms. It doesn't count the electrons. So even though water has 4 electron clouds around it, what happens is those extra electrons serve to kind of push down these 2 hydrogens because it has more electron density. They push down with greater force than the bonding electrons can push back. So that forces this into a bent geometry. So if I'm looking at my molecular geometry, a bond angle is the angle between the 2 adjacent bonds. If I'm dealing with 180 degrees, a linear molecule, then they are exactly as far apart from one another as they can be, which means they are on opposite ends of the center atom. If I push in a third one, that third atom pushes these down until the point where the two original atoms start to push against each other. When I finally get into the ideal situation, I'm in a trigonal planar situation. The bond angles are 120 degrees. Now, if I shove another molecule, if I shove another atom in here, Kylie, what do you think the bond angle is going to be?
109.5.
Ah, you cheater, you looked. Normally, If you shove another atom in here, you think, oh, well, that's just going to reduce it by 4. So the bond angles are going to be 4, and I'll have a square planar. But you got to remember, when you have 3 things, you can be 3 things define a plane. 4, you can invoke the 3rd dimension. So by invoking the 3rd dimension, you can kind of push this one up, and this one pushes these 3 down. So you have something called a tetrahedral. I shove another atom in there. I have 2 different bond angles. The bond angle for the planar molecules is 120. The bond angle for this one to this one is, or this one to this one is 90. Then if I have octahedral, shove another one in there, all the bond angles are 90 degrees. Any questions about it so far, ladies and gentlemen? Okay. If there are no lone pairs, around the center atom, molecular and electronic domain geometry are the same. If the center atom has no lone pairs, electron geometry and molecular geometry are the same. If you put a lone pair in there, that fusses with things. The electron domain geometry and the molecular geometry are no longer the same. So another important couple of slides coming up. If I have 3 electron domains, but I have 1 lone pair, this means I can't see one of the atoms and I have a bent molecular geometry. If I have 4 domains, the 4 domains dictate tetrahedral electron domain geometry. If I take one of these atoms away, replace it with a lone pair, that means I can't see it anymore. This means I have something that looks like a 3-sided pyramid, trigonal pyramidal. 2 lone pairs, I can't see the lone pairs. I have a bent molecule. If I have 5 things around my center atom and 1 is a lone pair, I get something that looks like a seesaw. I have these 2 here and this one here, and these can kind of go back and forth. Some chemists have a little more imagination than others. Trigonal bipyramid, 2 lone pairs, I get something that looks like a T shape. Trigonal bipyramid 3, I get a linear molecule because the 3 in the center plane get taken away first. If I have an octahedral, 1 lone pair, I get something that looks like a 4-sided pyramid, square pyramidal. If I have 2 lone pairs, I have something called square planar. And I just went through this quickly. I'm going to go through them individually in a second. So to get through VSEPR, to determine molecular geometries, you got to draw the Lewis structure first, have to draw the Lewis structure. Then you're going to count the number of electron domains. The number of electron domains on the center atom are going to dictate the electronic geometry. Then once you have the electronic geometry, you determine how many lone pairs there are, and that will dictate the molecular shape. Are we good, ladies and gentlemen? Two domains, it looks like that. They want to get as far away from each other. you're going to have a linear molecule. There are two electron clouds. Each of them are bonding. They push each other as far apart as they can. You have a bond angle of 180 degrees. There's only one molecular geometry, linear. If you do have a lone pair out here, it's still going to be a linear molecule because you only have two atoms. If I put three domains around the center atom, I have three electron clouds. This dictates trigonal planar. If they're all bonding, they push each other away equally at 120 degrees. If I have three domains, but one of them is a lone pair, that pushes the other two atoms down closer to one another, and we get a bent shape. Now, remember, what did we say the bond angle? Somebody answer this. What's the bond angle for three equal atoms around the center atom? Garrus, what's that bond angle? You're muted, Garrus.
120 degrees.
Okay. Now, remember, I said electron pairs push down with more force than bonding electrons. So when I have this, if I'm looking at the bond angle between the red ones and the blue one, what would you suggest that's going to be in relationship to the 120? Is it going to be more than 120? Is it going to be less than 120? Is it going to be equal to 120?
It's going to be 120.
Remember, I said that the lone pairs push down with more force than the bonding can push back.
Oh,
It's going to be less than 120.
less than.
For that reason, the electrons up here push down with more force, so that squeezes these two together a little more. So that bond is going to be a little less than 120. Similarly, if I have fluorine up here at the very top, and I have two chlorines down at the bottom, what has more electronegativity, fluorine or chlorine? Aaliyah, what has more electronegativity, fluorine or chlorine?
Fluorine.
So would you say, Aaliyah, that the fluorine has more electron density around it than the chlorines do?
Yeah.
So that too, because the fluorine has a greater electron density, it also will push down the two chlorines. So you would get a bond angle between the fluorine and the chlorines greater than the bond angle between the two chlorines. Again, is this all making sense? You with me yet? Or you want to go back to bed? Monica, you would look like you want to go back to bed. So if I want to break it down, if I have three bonding domains around my center atom, my molecular geometry is the same as my electron geometry. If one of those domains is an electron pair, I am going to get a bent molecule. I've already talked about this. 4 things around the domain. Let me just go back real brief. The geometry, the electron geometry around the center atom, just to make sure you understand that electron geometry is still trigonal planar, but the molecular shape is bent. I have 4 things around there. Electron domain, if I have 4 domains, that dictates that my electron shape is going to be tetrahedral. And again, they are going to repel each other 109.5, not the expected 90, because we're invoking that 3rd dimension. If all of them are atoms, then the molecular shape also is tetrahedron. Now, if I take away one of the atoms and replace it with a lone pair of electrons, I go from a shape of a tetrahedron to one of a 3-sided pyramid. So my electronic shape is still tetrahedron, but my molecular shape is going to be trigonal pyramidal. Three bonding, 1 lone pair. The thicker set of electrons that are up here are pushing down those atoms greater. So the individual bond angles between the terminal atom, the center atom, and the other terminal atom are pushed together. They're squeezed a little bit by the lone pair. So that bond angle is a little less than 109.5. Oh, don't know what I was thinking with this. If I have 4 domains on that center atom, but 2 of them are lone pairs. Again, I can't see the lone pairs. All I can see is the terminal atoms and the center atom. That gives me a bent molecule. Now, Kyle, when we went to this molecule, I said that that 1 electron pair pushed the bond angle a little less than the normal 109.5. Okay, Kyle? That's 1 lone pair up there. Now, when I do 2 lone pairs up here, predict the bond angle.
So it's usually what, like, would that be usually 120?
Nope,
And then
it's usually 109.5.
Gotcha. Okay, so if there's 2, then it's going to be like less than that. So I don't know, maybe like
Okay,
103 or something.
Not bad, Kyle. When I have 1 lone pair, it was 107.
Yeah,
If I have 2, do you think it's going to be more or less?
it's got to be less.
Because I've got more force. I got more electron density pushing down those 2 atoms. So
Yeah.
you get it down, you get that bond angle down to 104.5. Comparing the 2 bents, I have 2 bent shapes. One comes from a trigonal planar, one comes from a tetrahedron. Both molecular geometries are bent. Which one has the larger bond angle? Kyle, you're not allowed to answer. Maria, which one do you think has the larger bond angle? The one that started from trigonal planar or the one that started from tetrahedron?
The trigonal planar,
Why?
because
2 reasons. Give me one.
they're farther apart.
Okay, I'll
One.
buy that. I will buy that definition. Because originally, trigonal planar sets them in a plane. The original bond angles are 120. So they originally start at a larger bond angle. Anybody figure out what the second reason is? How many electron pairs are up here with the trigonal planar? Trigonal, what's trigonal mean? How many things?
3.
So if there are 2 of them here already that you see, how many electron pairs are up here?
1.
1. Tetrahedron, 4 things. How many electron pairs are around the tetrahedron?
2.
So in the tetrahedron, I have more electron density that's pushing those together even further. So I've got 3 examples with the tetrahedron. If I've got 4 bonding domains, no lone pairs, shape, electron shape, same as molecular, both are tetrahedron. If I have 3 bonding and 1 lone pair, electron domain, tetrahedron, molecular geometry, trigonal pyramid. 2 lone pairs, electron geometry, still tetrahedron, molecular geometry is bent. Questions, ladies and gentlemen? Okay, if I have a double and a triple bond, don't think triple bonds, don't worry about triple bonds, think double bonds. What happens is there's a greater electron density. Remember, it's the same thing as the fluorine having more electron density than the chlorines. So if the double bond has more electron density, that pushes down. The oxygen is pushing down on both chlorines, then the chlorines are pushing away from each other. So that also increases the bond angle between the chlorine, carbon, and oxygen over the chlorine, carbon, and chlorine. I get 5 things around. Trigonal bipyramid is my electronic shape. The bond angles, the ones on the plane in the center are 120 degrees apart from each other. The atoms up and down are 90 degrees away from the trigonal planar. You got 2 distinct geometry positions. Equatorial are the ones that are on the plane. Axial, that are the ones that are going up and down. So if I have an electron pair out there, I'm not going to exactly have 180 degrees anymore, but that's going to be pushed further so that there is a little greater distance because, again, the electron pair is pushing down on those. If I have 5 pairs and they're all bonded to atoms, I have a trigonal bipyramid molecule. 1 lone pair. 1 lone pair gives me something that looks like a seesaw. The poles are pushed slightly together. 2 unshared, I have a T shape. 2 of the equatorial pairs are unshared. If I have 3, I take the equatorial away and I have a linear molecule. So I have 4 possibilities with trigonal bipyramid. No lone pairs, electronic geometry, trigonal bipyramid, molecular geometry, trigonal bipyramid. 1 lone pair, Electron geometry, trigonal bipyramid, molecular seesaw. All the electron geometries are going to be the same. They're all going to be trigonal bipyramid. But if I have 2 lone pairs, I'm going to have T-shape. 3, I will have a linear molecule. Six pairs. There's only 3 examples here, guys. 6 pairs around the center atom, electronic shape octahedral. Equal angles, 90 degrees. If I take away one of the atoms and replace it with a lone pair, I have a square pyramid. I take 2 away, and I have a square planar. I've taken the 2 axial electrons away. So octahedral has 3 possibilities. No lone pairs, molecular shaped octahedron. 1 lone pair, square pyramidal. 2 lone pairs, square planar. Now, if you have a larger molecule, let me see who I want to talk about. Corey. You there, Corey? Would you bugger out on me, Corey?
Yeah, I buggered out.
Corey, what's the shape of this molecule? You got the Lewis structure in front of you. What is the shape of that molecule?
The whole thing. Could you describe it with just one shape?
Ah, good. You can't. If your professor gives you a molecule like this and says, what's the shape? If you're in the test, you take that test right up to him and you say, what do you mean by what's the shape? Which atom do you want me to use as the center atom? Because this particular molecule has 3 center atoms. Each one of them is going to give you a different molecular shape. This carbon has 4 domains, 4 bonding pairs around it. Therefore, the electronic shape around that carbon is tetrahedron. The molecular shape is tetrahedron. Let's look at the second carbon. Monica, how many domains around the second carbon? The one with the double bond oxygen.
3.
3. What does 3 domains mean? What kind of shape?
Trigonal pyramid.
Nope. 3 things make a plane. Trigonal. 3 things make a plane.
Oh, trigonal planar.
Trigonal planar. Guys, you're going to have to get those 2 straight. Trigonal bipyramid means there are 5 things around the center atom. This only has 3, so it's trigonal pyramid. So the geometry around that carbon is trigonal planar. Now, Alexis. Paige. Am I making you both absent for today? Kristen.
Yes.
This oxygen. What is the electron domain geometry of that oxygen?
Tetrahedral.
Tetrahedral. Okay. Now, what is the molecular geometry around this oxygen? Do I have lone pairs around that oxygen?
Yes.
So if I have lone pairs, do I see the lone pairs?
Yes.
No. Don't see lone pairs in molecular geometry. Okay, Kristen? So if I'm not seeing it, all I'm seeing is the carbon, oxygen, and hydrogen. What is the shape going to be? I don't know. It's a perfectly good answer. You're just having this stuff introduced to you.
I don't know.
Jeremiah.
I'm not sure either.
Okay, Kyle.
Sorry, what's the question?
We've already established, there are 4 things around this oxygen. So the electronic shape is tetrahedron. The question I just had to you is, what is the molecular shape if if 2 of those things are lone pairs?
Bent.
Bent. Okay. Jeremiah, Kristen, you get it?
Yes, sir.
Okay. Now, I have to get through one thing because this is part of the lab that's coming up. Polarity is a property of a molecule that when it is introduced into a magnetic field, the molecule will orient it according to that molecular field, which means there is a negative end of the molecule and a positive end of the molecule. So that the negative end of the molecule in a magnetic field will be attracted to the positive pole. The positive end of the molecule will be attracted to the negative pole. Is that making sense so far? Making sense so far? Natalie, we good? T, does that make sense, T?
Yes.
So, polarity is also the property that dictates solubility. Because if something has charges on it, it's going to be attracted to something else with charges on it. So that a polar solvent will dissolve polar compounds and ionic compounds because both the polar and ionic compounds have charges to them. Nonpolar, non-charged dissolves nonpolar substances. Now, if I'm talking about bond polarity, because different atoms have different electronegativities, we are getting a difference in sharing the electrons. If I have a fluorine next to a hydrogen, fluorine is much more electronegative than the hydrogen. So the electron's going to want to spend more time around the fluorine than it does the hydrogen. Therefore, I get a bond polarity. There's a negative side to the bond and a positive side based upon how much time the electron spends on the particular atom. Gone through all this. So if I have an HF molecule, I can designate that this is a polar bond by either making an arrow with the head going in the direction of the negative charge, or I can put this small gamma positive, small gamma negative. Either way, that's just telling me that this bond is polar and I got a negative side and a positive side. Now, back in medieval times, they had this quaint little custom called drawing and quartering. And basically what they did was they tied a limb of the person to each one of 4 horses and they yelled, "Giddy up." When they did that, did the torso move? If each one of the horses is pulling with equal strength, is the torso going to move? Jeremiah, you've done physics and vectors. If each one of those horses is pulling with equal strength and it tears off a limb, the torso that's left, is it going to have moved?
Yes, it would have moved.
I don't mean going down. If they're pulling with
Oh.
equal strength, if they're pulling with
Then it's
equal
not going
strength,
anywhere.
it's not going anywhere. Same thing happens in chemistry. If each one of the bonds is pulling with the same force and are equally distributed, then even though you have polar bonds, because the force is equally distributed, that molecule is not going to move. All right. Say we have a carbon in the center, and we have on the outer edges 4 chlorines. Now there is a polar bond between the carbon and the chlorines, but it's entirely symmetrical. So even though each one of those 4 points is negative, if I move one of the negatives towards the positive end, that's forcing another one of them closer to the negative. So it pushes back. So that when we have this overall symmetry, we don't get a movement of the molecule in a magnetic force. Even though the molecule has polar bonds, the overall effect on the entire molecule is that it is nonpolar. If I have a carbon dioxide, and oxygen certainly is more electronegative than carbon, so I have both of these ends are equally negative. If I put this in a magnetic field, if this end is attracted to the positive pole, then this end is going to be repelled by the negative pole. So I don't get any movement. An entirely symmetrical molecule, non-polar. So there are 2 things I need to have molecular polarity. I need to have a polar bond, a significant difference in the electronegativities of the 2 elements within the bond. The other thing I need is that the molecules must be asymmetrical. I have water. I have an oxygen, and I have 2 hydrogens. Each one of these are polar bonds, so that I have a negative oxygen and I have a positive side. Is this molecule symmetrical? Let me see who I can pick on. Bethany. I haven't picked on you yet, Bethany.
I don't know.
Is it symmetrical? Well, look at it. You know what symmetrical is, don't you, Bethany?
Yeah, I do. It looks symmetrical, but I'm wrong about a lot of things. So,
Okay, well, let me ask you this, Bethany. Is the top side of this molecule the same as the bottom side?
okay, no, I didn't know. That's what no, it's not.
So is this molecule symmetrical?
No.
So it has polar bonds and it is asymmetrical. Is this molecule going to be polar? Let's go back to here. To have molecular polarity, what are the 2 requirements? Bethany?
Oh, sorry, I didn't know it was still me.
Yeah.
Yeah, it's gonna be polar.
I have a difference in electronegativity. I have a polar bond between the oxygen and the hydrogen. So I have polar bonds. It's asymmetrical. This is going to be polar. HCl. Not symmetrical. Got a polar bond. It's going to be polar. Carbon tetrachloride. I got this one pushing up the same amount as these 4 are pushing to the sides and pushing down. entirely symmetrical, nonpolar. Ammonia. I have polar bonds. Is this symmetrical, Kristen?
No.
Not symmetrical, polar bonds, it's going to be polar. What about this one? Jeremiah. Is this one symmetrical?
Yes.
But I have a chlorine on top and 3 hydrogens. Are they the same, the top to the bottom?
Oh, no, they're not.
So if it is not symmetrical, if it's asymmetrical and I have a polar bond, will it be polar? Again, go back to this slide. What are the 2 things I need to have a molecular polarity? I need to have a polar bond and it needs to be asymmetrical. Are both requirements there for monochlorotrihydrogen, trihydride? Jeremiah?
No, they're
Okay.
not.
What is not set? Does it have a polar bond?
It has a polar bond, but it's not symmetrical.
Yeah, that's what it's requiring, Jeremiah.
Right.
If it's asymmetrical, if it's not symmetrical and it has polar bonds, then the molecule will be polar.
Oh, okay.
Not symmetrical and polar bonds, molecule is polar. If it is symmetrical and has polar bonds, then it is not polar. If it is even asymmetrical but no polar bonds, that's also going to be non-polar. SO2. Let me do this. I need to write these down. I'm just going to do SO2 and SF6. Okay, that is the Lewis dot structure for SO2. What is the electronic shape? Garris? Electronic shape of SO2.
Trigonal planar.
Trigonal planar, okay. Is this, okay, trigonal planar, what is the molecular shape?
Angular.
Bent, angular or bent, you can call it angular, that's fine. All right. Does this have polar bonds, Garris?
Yes.
There's a difference in electronegativity between the O and the S. Last question. Is it polar?
Yes.
It is asymmetrical. And because it is asymmetrical, because it's asymmetrical and has polar bonds, it is a polar molecule. Now, if I do another molecule, I'm going to do my best to draw this. Here, undo. hexafluorosulfur. Or hexafluorosulfide, sorry. Looks like that. Natalie, what is the shape? What is the electronic shape?
Is that octahedral?
Octahedral. What is the molecular shape?
Octahedral.
No lone pairs. The molecular shape's the same as the electronic shape. Okay. Now, are there polar bonds, Natalie?
Yes.
All right. Is the molecule polar?
I would say no.
But it has polar bonds.
Oh,
I'm tricking you, Natalie. Stick
Oh,
to your
okay.
guns. Why is this not polar?
because it's symmetrical. It has the same electronegativity.
Absolutely. This is entirely symmetrical. This would not move in a magnetic field. And that's basically, guys, that's really all I have to say about this. I don't think that I need to go any further with it. I may need to talk about one other thing because he may have put something in here. Okay, granted, as I said before, this is going to be a pain. There are 90 questions, guys. 90 questions on this. He gives you various examples. So there are a lot of things in here. I'm not seeing. Oh, thank you. I'm sorry. He does give you a lot of information down here. It would be a good idea to look through those because Dr. Musgrave is good about his explanations. All right. Start quiz. Okay. All right. Each one of the compounds are going to have the same questions. You're going to need to draw the Lewis dot structure. First question. Be aware of this, ladies and gentlemen. And if you have questions when you're on your test, ask your professor to be sure. Sometimes professors will ask how many lone pairs are on the center atom. Sometimes they will ask how many lone pairs are on the entire molecule. Be aware of that before you answer the question. If you have any doubt, ask him what he means. In this particular example, on every question, he is asking you how many lone pairs are there in the entire molecule. Second question. All right. Now, this is going to be a 4-part question. And you have to answer it in this fashion. First question, how many electron domains does H2O have? Come on, we've done this molecule here along. Kylie, do you remember how many it has?
4.
4. So the answer to small I, you got to find one that begins with 4. Number of atoms bonded to the central atom. Kylie?
2.
2. All right. Now, how many electron pairs attached to the center atom? Remember, I told you, you have to be aware of what the specific question. For question 2, they want the specific number of lone pairs on the center atom. So Kylie, how many is that?
2.
So I want 4, 2, 2. Now, here it becomes a little tricky. And I don't know why he's doing this because you've already answered the question. When you see an A, the A stands for the center atom. If you have an X, that means atoms bonded to the center atom. So in this first example, this means there are 5 atoms bonded to the center atom. If you have an E after that, those stand for lone pairs. So the A would be the center atom. This one has 3 X's, 3 atoms attached to it, plus 1 lone pair. This one has the A center atom, 1 atom attached to it, and 2 lone pairs attached to the center atom. Are you kind of getting, anybody confused about this? Are we good, guys, with this? Question 3, what is the overall shape? Damn it, I have to go through that. Okay. Somebody remind me hybridization. Okay, he wants the electron group geometry, which is the overall shape, and the hybrid orbital designation, which I'll tell you in a second. So in water, what is the electron group geometry or the electron domain geometry? I don't want to wait. Come on, somebody yell it. Come on.
Trigonal?
Nope.
Linear?
Kylie? Nope.
Tetrahedral.
Tetrahedral. There are 4 things, 2 lone pairs and 2 hydrogens around the oxygen. So the electron group geometry is going to be tetrahedral. And I will get into hybridization in a second. But that also is going to be sp3. The next shape, sorry. Okay, we've established that the electron geometry is tetrahedral, but 2 of the spots are occupied by lone pairs. So it's not going to have a tetrahedral shape. What is the shape going to be?
Bent.
Bent or angular? Last question. Is it polar? Is water symmetrical? Thank you, Kylie. Say it out loud.
No.
Water is not symmetrical. Does it have polar bonds, Kylie?
Yes.
So the fact that it has polar bonds and asymmetrical, is it polar?
Yes.
And you're going to need, again, there are 19 questions or 19 structures. All of the questions are the same for each structure till you get down to 18 molecules, question 90. Any questions about the results other than the hybridization that I'll get into in a second? Okay, I'm going to do a real rough and quick on the hybridization. I did not mean to do that. That's not what I wanted. I'm not going to go into the theory behind hybridization. I'm just going to tell you how to determine what's hybridization. And I just need the one slide. Okay. Basically what hybridization is you take atomic orbitals and you mix them together to make a hybrid. It's kind of like taking a donkey and a mule and making a, what is it? Donkey and a mule? No, it's something and a donkey and a horse and making a mule. Okay? A mule is a hybrid animal. It's like a liger. Okay? Hybrid animal. So we have the ability to do something called hybridize atomic orbitals. Okay? Now, if I have two things, two electron geometry, two electron domains around a center atom, I need two hybrid orbitals. So I take an S and a P, hybridize them to make SP. If I have three electron domains, that means I need three hybrid orbitals. I take an S and two P's. So that becomes sp2. If I have four electron domains, I need four atomic orbitals, an S, a PPP, or sp3 hybridization. Now 5, remember I said we invoke the d orbitals? If I have 5 domains around the center atom, that means spp 1d. So that becomes sp3 dehybridization. Octahedral geometry, 6 things, spp dd, sp3 d2 hybridization. And Kristen, you just look like you're just about done for the day. Go back to bed, Kristen. No, stay here. I need to discuss something with you. Any questions, guys? Okay, I'm going to stop share and I'm going to go back. Do you have any questions about hybridization? It really is that simple. You look at the number of the electron domains. That number is the number of atomic orbitals you need to put in there. And it goes in that order. S's, then the P's, then you add the D's. Okay, show slides. Exit preview. Course content. I think the post lab is just something similar to the results, if I remember correctly. But we'll go through it just to be sure. Again, this is going to be fairly lengthy. Number of valence electrons in NH2Cl. Anybody have any question about that? How many lone pairs? How many bonds? Shape excluding. In other words, they're looking for the molecular shape in this question. Oh, it's not as bad as I thought. Last question, is it polar? So the post lab's not that big a deal. I really would suggest that you do this lab because it will give you lots of practice in drawing Lewis dots and being able to organize the VSEPR aspect of it. Any question on this lab? It is due next Sunday. I'm sorry, yeah, next Sunday at midnight. That's when your labs are due, aren't they? Sunday at midnight? All right, let's talk about the test, ladies and gentlemen. I know I am, as a lecturer, I'm giving 2 tests next week. Is that pretty much what the rest of you are going through in your schedules? Talk to me, guys. I'm trying to make life easier for you. Are you also having a third test and a final next week? Guys, I need you to unmute. Everybody unmute right now, because I need you to verbalize what I am proposing. And this has to be 100% or not. I have to have complete cooperation with this. I am willing to give you the lab final on Wednesday. This would alleviate some of the conflict you'll have by having to study for a lab final and a lecture final test on Monday. Talk to me your feelings, guys.
Would VSEPR still be included on the final if we
Yes.
take it Wednesday? Okay.
Yes. I can't eliminate questions.
I personally honestly still lean towards having it on Monday, because then at least we have more time to prep for it. I mean, I can understand wanting to take it this Wednesday, but it seems kind of like the same material that's going to be on test 3 anyways. So I can kind of study for it together, and then just go back on some of the past labs and stuff.
By the way, that Kyle makes an excellent point. If you're studying for the lab, you are literally studying for the final as well. Because think about all the labs that we have done. The other advantage to having it on Monday is I will be here on Wednesday. I will open the class up for a review. But that review is going to depend on you. It's going to be entirely student generated. I'm not going to have anything really prepared. The best way for you to study for this final is to literally go through and recalculate all of the calculations you did for the results section. That is the basis of the questions on the final. And again, it will help you for your lecture final, because you're getting practice at this. Having said that, I'm getting the general gist. I've only had one person make any comment, and that was against having it on Wednesday. So thank you, Kyle, for making me bust my ass next week and do 2 test corrections in one night. Thank you so much, Kyle.
You're very welcome.
No, I'm happy to do it. I just want to accommodate you guys, and I thought I would offer this. So, bottom line, you have heat of vaporization due on Tuesday night at midnight. Results post lab. You have by next Sunday, midnight. You have this lab results post lab. We are going to put the final in, and I will be grading. I have to get that turned around quicker than the other one. So I am going to be working my butt off next Tuesday, and I will have the final grades in by next Tuesday for the lab. Any questions, guys? Okay. I will see, by the way, it's not mandatory. Attendance is not mandatory on Wednesday. So if you want to sleep in, go for it. And definitely next Wednesday, sleep in. The test will be conducted at this time next Monday, though, because I got to get these things turned around real quick. So you will have the test from 8 until 11 next Monday.
Do we have to join like a Zoom call or something?
Honor lock.
Okay.
It's it is already in there, and the honor lock is already prepared. Okay, so it's actually, you guys aren't used to this because you haven't done honor lock all semester. Is anybody unfamiliar with honor lock at this point of the COVID epidemic? Do I need to do a practice honor lock exam? And by that means, it's just you get prepared to go on honor lock. There are no real questions. It's just you get prepared with what you have to do going into honor lock. Does anybody need that? Please speak up now. Does anybody have any accommodations? If you do, please stay after class, or rather than that, if you would like to, please email me that you have accommodations. Other than that, guys, I think I've covered everything. It really has been a fun time this semester, guys. And that's hard to say about a summer class. It really has been good. Okay, with that having said, guys, I will see some of you on Wednesday. The rest of you, good luck to you in the future.
Thanks, Mr. P.
Take care, guys.
Thank you.
Thank you.
Thank you.
I did have a question.
Of course,
Just about.
Gareth, I'm sorry. I would have been disappointed had you not had a question.
Okay, yeah, so for the lab book, I just want to make sure there aren't really chemical hazards.
No,
There-
Gareth. Don't even worry about it. You'll get to 10 points. You'll get to 10 points. You're going to need to fill something. Oh, damn it. I got to do, I'm sorry. Basically, I have to tell you that you're allowed to have your notebooks. You're allowed to have your notebooks, and I will send an email out to that effect.
Okay.
So you are allowed to have your notebooks for the final. I'm not going to check this. Be honest with you, if you've noticed, I haven't been really checking the last couple. All I wanted to do was establish that you knew how to do a notebook. So literally speaking, Gareth, put in the notebook what you want to. I'm not going to be grading it.
All right. Thank you.
You're welcome. Corey, you left for a while. Corey? Corey?
Yes.
You're going to get an email in a second or two. I forgot to tell you guys that you are allowed to use your notebook in the final. Okay? So I'll send out an email. It'll be a message to that effect. All right?
All right, cool.
Anything else, guys? Jeremiah?
I have two things. So first thing is, how long is this test? Is it 2 hours?
It'll be 3 hours.
About 3 hours? Okay, so I probably won't need the accommodation. But I had a question about the previous lab. I'm just curious to see, so at all my calculations, I knew that the slope was correct. It was around like negative 2,200. When I did the calculations, I ended up with a change in H of like 18.76, which left me with an error of around 57%. So, and no matter what other calculations I do with this number, all of them lead to errors well above 100.
Jeremiah, have you submitted it yet?
No, I have not.
Okay, the best thing to do would be to take a picture of your calculations. I'll look through it and see what you've done. did you remember to change R to kilojoules or change your slope divided by R to kilojoules?
Yes, I did.
Um,
Here, let me do this real quick.
I'd rather not do it right now,
Scroll.
Jeremiah.
Oh, okay.
I'd rather not
worries.
do it right now because for a couple reasons. One of which is you'll see me floundering around.
Mhm.
It happens when you're trying to evaluate somebody's calculation. You'll see me floundering around for a while, whereas I don't have to waste your time and I can look at your calculations at a later date. And
Okay.
that seem reasonable?
Yeah.
Okay, let's do it that way. Just take a picture and send me an email with the attachment.
Okay. We'll do.
Okay. I
All right.
will see you later this evening.
Yep. Sounds good. See you.
Take care.
You too.